Hello friends and welcome to average classes. Okay, so we have come to the part 3 of your fluid kinematics where we will be discussing the velocity and acceleration. Okay, and we have already discussed velocity, acceleration, pressure, whatever we are finding that at a point. That point we are that is the point of our interest. Okay, we are deciding the point. This is your Eulerian approach, and from here onwards we are only following the Eulerian approach and we are not following the Lagrangian approach. Okay, so and yes, if you haven't subscribed to the channel yet, please do subscribe. Okay, so now let us say this is my streamline. Streamline we will be discussing in future classes. Okay, and at any point on the streamline gives the direction of the velocity. So this is my direction of velocity v, tangent to the streamline gives your direction. So let us say this is the point and point is P, whose coordinate are x, y, z. Okay, x, y, z are the coordinates of the point P. So that means if I will draw the point like this, see, this is the z axis, this is your x axis, this is your y axis. So this is somewhat like this. Okay, are you getting the point? So from x axis it is at certain distance, from y axis it is some distance, and from z axis it is some other distance. Okay, let us say x axis it is at a distance of x, y axis it is at a distance of y, and z axis it is at a distance of z. That's why the point coordinate is x, y, z, isn't it? And so this v is moving in the space. Okay, this v is moving in a space. That means three-dimensional. Space is three-dimensional. So it has some component of velocity along the x, along the y, and along the z direction. Okay, so it has some component of the velocity along x direction, component of velocity along y direction, let us say component of velocity along x, y, and z direction. Let us say the component of velocity along x direction is u. The component of velocity along y direction is small v, and the component of velocity along z direction is your small w. Okay? So how we are gonna represent this v? V is what? A velocity. V is the velocity vector. What is this? Our field variable. V is the velocity vector field variable. What we have wrote? Sir, you have wrote V, which is a velocity vector field variable, is nothing but ui cap plus vj cap plus wk cap. This is your velocity V. Then what will be its magnitude? Sir, magnitude will be u square plus v square plus w square under root u square plus v square plus w square under root. Very good. What is u? Sir, u is nothing but x component of velocity. X component of velocity capital V. What is your small v? Sir, the small v is y component of velocity v. And what is your small w? Sir, small w is the z component of your velocity v. Okay. So this v, capital V is a function of space and time. That's what we have discussed. The capital V is a function of space and time. That means this all will be u, v, w. They all are also function of space and time. So this is u also a function of space and time. V also a function of space and time. Also the W is also a function of space and time. Understood? So this is how you represent your velocity vector or velocity field variable. Its magnitude and the vector field. Okay, this is the magnitude. Whatever unit you are writing, meter per second, whatever unit is given, same unit only will write it. Okay, meter per second. Let us say for the time being we are taking velocity unit is meter per second only. Okay, so this is your velocity. Now what is my acceleration? Sir, acceleration is change in velocity with respect to time. Change in velocity with respect to time. But here how many variables here? Sir, you have so many variables. That's why I cannot go for direct differentiation. Total differentiation I won't go for. So what we have to take? Partial differentiation. So if I write the change in velocity dv, the change in velocity dv, what it will give me? Sir, it will give you dou v by dou x into dx plus dou v by dou y into dy plus dou v by dou z into dz plus dou v by dou t multiply dt. Multiply dt. Very, very good. Very, very good. Okay. So this is your dv. What is your acceleration? Sir, acceleration A is equal to dv by dt. Acceleration A equal to dv by dt. See, you have drawn this diagram. So I am erasing it. I need some space power. So I have to use certain space, hence I have to erase it. Okay, I hope you understood that, right? X component of velocity u, y component of velocity v, z component of velocity w, all are small. So dv by dt. Now write re baba, multiply dx by dt plus dou v by dou y multiply dy by dt plus dou v by dou z multiply dz by dt plus dou v by dou t multiply dt by dt. Okay, now you tell me, limit your dt tends to 0 dv by dt. What is this, sir? This is your acceleration. This is what your, sir, this is my acceleration. Okay, or your limit dt tends to 0 ds by dt. Sir, we have studied this, our velocity, that is your capital V. For capital V is a function of x, y and z, isn't it? X, y, z and t, space and time coordinate. So your limit dt tends to 0 dx by dt, that is the movement along the x direction. What is that? Sir, this is our x component of velocity, sir, small u. Very good. So similarly, you take limit dt tends to 0 dy by dt. What is this, sir? This is y component of velocity v. Arey wah. Similarly, limit dt tends to 0 dz by dt. What is that? Sir, this is the z component of velocity, that is your small w. That is your small w. Now put these things here. So what you got? Acceleration A equal to, this thing I am writing first. Okay, here I am writing first. What you are getting? Sir, I am getting dou v by dou t plus dx by dt. Sir, u. So u dou v by dou x plus v dou v by small b, v dou v by dou y plus w dou v by dou z. This is what finally, remember this all are what? Vector. So you have to give the vector symbol. Okay, if you are not giving also, it's understood. Okay, so u dou v by dou x plus v, this is your velocity vector. This capital V is the velocity vector. U, v and w are the component of velocity along x, y and z direction. Component of velocity along x, y and z direction. So this is your acceleration. This is your acceleration. Here you might observe there is a term. This particular term, what is your, with respect to time, the change in velocity with respect to time, we call it as local acceleration. We call it as local acceleration, or it is also known as temporal acceleration, and it is also known as temporal acceleration. Very, very good. Very, very good. So, and this component of velocity, this particular term of your acceleration, this is what? With respect to space x, y and z. With respect to space x, y and z, this is known as your convective acceleration. So, the component of velocity along the space direction is known as your convective acceleration, and the component of velocity along your with respect to your time is your local acceleration. With respect to space, your convective acceleration. They ask in exam. We'll be solving some numericals. Okay, but for now, you pause the video, note it down. Pause the video and note it down. The velocity and acceleration. Local acceleration and temporal acceleration. Okay, that is the rate of change of velocity with respect to time at a given point in a flow, which is your local acceleration, and rate of change of velocity due to position change in a fluid particle is your convective acceleration. So we got this term now. So this is what sometimes they will write as d by dt. This is also known as your material derivative. What? Material derivative or your total derivative. or total derivative. This term though you know that this is your partial derivative. Partial derivative. Okay. So now you got your A. See, velocity has also x component, y component and z component. Similarly, your acceleration also has your x component and y component and z component. So if I have to represent your acceleration A, I will represent like this. That is your ax I cap plus ay j cap plus az k cap. So what will be its magnitude? Sir, its magnitude is going to be ax square plus ay square plus az square, right? Whatever you need. Normally meter square per second. That will be your meter per second square. That is your unit. That is your unit, meter per second square. So acceleration also has x component, y component and z component, and each has a local acceleration and a convective acceleration. So follow me when I am writing it carefully. Okay. So your ax, that is the component of acceleration along x direction. What is the velocity along x direction? What is the velocity along x direction? U. So what will be ax here? Like that, if I write ax is nothing but limit dt tends to 0 du by dt. So what will be your ay? Sir, this is limit dt tends to 0 dv by dt. What is your v? Sir, velocity along y direction or y component of the velocity. So what will be your az? Sir, limit dt tends to 0 ub w dw by dt. So now this u is a function of u is a function of x, y, z and t, and v is a function of v is also a function of space and time, that is x, y, z and t. W is also a function of x, y, z and t. So similarly, now your ax also is a function of fy, x, y, z and t. Ay is also a function of x, y, z and t, and az also is a function of x, y, z and t. That is space and time. So what it will become? Del u by del t plus u del u by del x plus b del u by del y plus w del u by del z. Again, need not to say this is which component of velocity, sir. This is the which component of acceleration? Convective acceleration. What is this? Local acceleration. So what is your ay? Sir, ay is d dou v by dou t plus u dou b by dou x plus b dou b by dou plus w dou b by dou z. Similarly, az dou w by dou t plus u dou w by dou x plus b dou w by dou y plus w dou w by dou z. So this is which component of velocity? Sorry, which acceleration? So this is your convective acceleration. What is this? Sir, local acceleration. Okay. So when they are asking to calculate acceleration, you have to calculate x, ay, az and proceed. So is it going to be this much hard? See, normally in GATE they will give you a two-dimensional flow. That means either xy or yz or xz they will give. Let us say they have given x and y. If they have given x and y, so dive az over. This portion is not required. They will tell you the flow is steady or something. So this portion will be not required. Because it is a two-dimensional flow, this also you won't be calculating. So if there is a question of two-dimensional flow, that is only x and y direction, so O and steady, we'll discuss what is steady. Okay, so you only need to calculate this much. Only 4 terms you will be calculating in such cases. Okay, which is normally what they ask in your exam. So it is easy, don't worry. Don't get tense because of this. We are going to solve some numericals. Okay, pause the video, note it now. Now we are discussing when a fluid particle is moving in a curved path. Okay, and we'll take a streamline. So streamline you are mentioning again and again. Yes, streamline we will be studying in our next chapters. Okay. For the timing, you remember streamline is a line where the tangent at any point gives the direction of the velocity. Okay, gives the direction of velocity. Let us say this is your streamline, which is moving in a curved path. So this is the curvature done. Okay, and its radius is nothing but radius of curvature of the streamline. So this is your particular point is here. If I draw a tangent of this, okay, so this will give me a tangential acceleration. See what happens in a curved path, the direction changes, the direction of the velocity changes continuously. The direction of the velocity changes continuously. So the direction which is normal to it is nothing but my normal acceleration. Is nothing but normal acceleration. So when a fluid particle is moving in a curved path, we have two components of acceleration. One is your tangential component of acceleration, another one is your normal acceleration. Okay. So the tangential acceleration is due to the change with respect to space, or change with respect to time, or change with respect to both space and time. In such case, your alpha S formula is this. Okay, dou Vs by dou T plus Vs dou Vs by dou S. What is Vs? Tangential component of velocity. In normal acceleration, it is doubled because it is moving in a curved path. That means simply due to the change in direction of velocity, and regardless the magnitude of the velocity is changing or not, we are not bothered. Here the magnitude of velocity, here we are not bothered about the magnitude of velocity, but we are taking care of the change in direction of the velocity. That's why the normal component of acceleration is coming. Okay? So in this case, alpha n equal to this. So hence what we came to know, sir, you were talking about acceleration. Now you say two types of acceleration. One is your tangential component, another one is your normal. Again tangential, here we have two, local and convective. Normal also we have two, what? Local and convective component of acceleration. What is the local component? Local tangential acceleration, sir, dou Vs by dou T. Okay, what is your convective tangential acceleration? Sir, Vs dou Vs by dou T. That is previously what we wrote. That is the tangential acceleration. What previously we wrote? You wrote Ax equal to dou U by dou T plus U dou U by dou X plus V dou U by dou Y plus W dou U by dou Z. That is nothing but your tangential component of acceleration. Normal is this. What is the local normal component of acceleration? Sir, dou Vn by dou T. What is convective normal component of acceleration? Sir, it is Vs square by Vs square by R, when R is the radius of curvature of the streamline. Okay. So again, in such cases, what will be your acceleration? Sir, in such cases, my acceleration alpha will be equal to alpha S square plus alpha n square under root. This will be your acceleration. Okay, alpha S square plus alpha n square under root. Very good. Note it down. Next, what we want is, we want to know the acceleration for a steady flow, unsteady flow, uniform flow, non-uniform flow, or steady uniform flow, steady non-uniform flow. So these are the things we wanted to know. So hence we'll have a detailed steady and unsteady we'll study in our next topic, that is types of flow, detail. But okay, what is a steady flow? If the flow property, velocity, acceleration, pressure, these flow properties do not change with respect to time. Do not change with respect to time at a particular point in space. Means what, sir? Okay. See, here I have took a convergent divergent nozzle. Let us say the velocity at this point is 150 meter per second. The velocity here is 300 meter per second, and the velocity here is 400 meter per second. This is your velocity at three space. See, at a particular point in space. So I have took 3 cross section, AA, BB, CC. So during time t equal to t0, my velocity at AA was 150 meter per second. The velocity at BB point was 300 meter per second, and velocity at C point is 400 meter per second. This is I have took a convergent divergent nozzle. Okay. Do not change with respect to time means now I have changed the time. Time change, t equal to now t1. So at time t equal to t1 also, at point AA, if the velocity is 150 meter per second, at point BB the velocity is 300 meter per second, and point CC, the velocity is 400 meter per second, then such a flow is known as your steady flow. What I change? Time I change. T0 to T1 I think. AA point 150. Here also AA 150 only. BB 300. Here also BB 300 only. At CC cross section 400. Here also 400 meter per second. That means if you change, even if you change the time at a particular space, the velocity what is flowing is same. And such a flow we call it as steady flow. Do not change with respect to time. Do not change with respect to time. So this is our what? Acceleration. What is this? Sir, this is local acceleration. What is this term? Sir, this is convective acceleration. This is convective acceleration. So you tell me for a steady flow, what will be there? What will be your local acceleration? Local acceleration is 0. Convective acceleration will be there. Okay, for a steady flow. For an unsteady flow, sir, unsteady flow, both might be there. Okay, so for a steady flow, local acceleration is 0. That's all we know. Okay, now coming to your which flow? Uniform flow. Okay, now coming to your uniform flow. Uniform flow, what did it say? It is the flow where the flow properties do not change from point to point in a space at a particular instant of time. Means what? Okay, so I have took here t equal to t0. What I have done? T equal to t0. What happened? I have checked here. The velocity is 5 meter per second. I have checked other point, that is also 5 meter per second. I have took at the here also I have got 5 meter per second. So throughout the space at any particular instant of time, that is your t equal to t0, if your velocity is same throughout the space at any time, if the velocity is same, we call it as what? Uniform flow. That means suppose at t equal to t1, here I am getting 7 meter per second. Now in this place also 7 meter per second. Here also 7 meter per second. So this is also uniform flow. At any given instant of time, if velocity is not changing along the space, any space, wherever you take, the velocity is constant throughout. So we call it uniform flow. So at uniform flow, velocity is not changing along which direction? Space direction. So what will happen to the convective acceleration? 0. What will happen to the convective acceleration? 0. So in a uniform flow, see, okay, local may be there, we'll discuss that in detail, but convective acceleration is 0. So this is also I am writing as like this. Okay, we'll discuss that. Why? Now in a non-uniform flow, local may be there, but convective is definitely there. Okay, convective is definitely there. Okay. Understood? Steady flow which is 0, local acceleration 0. Unsteady flow, nothing like that. Uniform flow, convective acceleration is 0. Uniform flow, convective acceleration is 0. Okay, pause the video, note it down. Good. Very, very good. So, I am erasing this. Now see. Suppose here 7 meter per second you have Let us say I am changing that value. I am changing the value at time t equal to t1 also. Here I have 5 meter per second. Here also 5 meter per second. Here also 5 meter per second. So now see, you change the time at any given point. That is your these 3 points. What happens to the velocity? Velocity is same. It has not changed. Means it is what? Steady flow. It is steady flow. At the same time, velocity is constant throughout. Means which flow? Uniform flow. Means which flow? Uniform flow. So this kind of flow is known as where your velocity is neither changing with respect to time nor changing with respect to space. That kind of a flow we call steady and uniform flow. Steady and uniform flow. So what will happen to the local and convective acceleration in such case? Which case, Baba? Sir, steady, uniform. Good. So steady and uniform flow. uniform flow, what will happen? Local acceleration 0, convective acceleration 0, hence what happens to the total acceleration? 0. Velocity is not changing only. What happens if it is your unsteady and uniform flow? Sir, unsteady flow, so local acceleration is there, convective acceleration 0 because uniform flow. Okay, what happens if it is steady flow and non-uniform? Steady and non-uniform. Sir, steady and non-uniform. Acha. Steady means local acceleration 0, convective will be there. What if it is unsteady? If it is unsteady and non-uniform flow. See, unsteady, non-uniform. So it has local acceleration as well as the convective acceleration. So in case of a steady uniform flow, the total acceleration is big under 0. In case of a steady uniform flow, the total acceleration is 0. This is what I wanted to convey. This is what I wanted to convey. Okay, so with this, your kinematics chapter 3 over. Kinematics part 3 of over. Next class will be dealing with types of flow. Okay, and I'll see if I can do some problems of this acceleration term also. Okay, so all the very best. Thanks for watching. Okay, and if you haven't subscribed to the channel yet, please do subscribe. Thank you.